Welcome to the Deep Dive. We sift through complex topics to bring you the essential insights. Today, picture this, the roads in the United States. Just try to imagine the sheer scale. Any guesses? It's a staggering 8.5 million lane miles. That's hard to grasp, right? Think about it like this, 19,300 square miles of pavement. Or maybe picture 9.4 million American football fields, Lambeau, Jerry World, take your pick. Or nearly 7 million soccer fields. It's just a huge amount of hard surface. And that's really the problem, isn't it? These vast impervious surfaces, they don't let water soak in. So they contribute massively to urban runoff, pollution, even making our cities hotter, that urban heat island effect. Okay, let's unpack this. Today, our deep dive is into porous pavements. It's a really innovative idea in low-impact development, or LID, basically rethinking roads and water.
Exactly. And our mission for you today is pretty clear. We want to explain how these pavements actually work, what are the real benefits, what are the limitations, and where can they really make a difference for our cities and our environment. If you're interested in environmental solutions and sustainable infrastructure, this is your shortcut to getting up to speed.
So let's start back with that huge number, 8.5 million lane miles.
Yeah.
That figures from the Federal Highway Administration, the FHWA. And when they say lane mile, it's useful. It means one lane, usually about 12 feet wide, for 1 mile. It just helps standardize things, focusing on the sheer area of pavement out there.
And the vast majority of that area, those millions of lane miles, are impervious. Like you said, they're designed not to let water through, just like a lot of roofs on buildings, actually. So rain hits, it runs off, carrying pollutants, overwhelming storm drains. It's a significant issue.
Right. So if impervious is the problem, porous pavements offer a fundamentally different approach. They literally let the water pass right through the surface. We're mainly looking at 3 types today: porous asphalt, porous concrete, and then things like permeable pavers or bricks.
And the really fascinating thing, the core design principle, is something called gap gradations.
Gap gradations. Okay, what does that mean?
Well, traditional pavement, what we call dense graded, uses a mix of different size stones and fine particles packed tightly together. The goal is maximum density, minimum voids, maybe only 4% air voids.
Okay, super compact.
Exactly. But with gap gradation, they deliberately leave out certain sizes of aggregate, certain sizes of stone. This creates a hole in the structure, if you will. It results in much higher air voids, maybe 15% to 25%.
So it's intentionally porous.
Precisely. And those interconnected voids are what allow the water to flow through so easily.
Okay, that makes sense. And once you get that, the benefits become pretty clear. First off, obvious one, runoff reduction. Water goes through the pavement, not over it.
Yeah.
So you don't get that massive surge, overwhelming storm drains during a downpour.
Right. Less localized flooding, less strain on infrastructure.
That then pollution control.
Yeah.
And here's where it gets really interesting, I think. Picture a big parking lot, like a Walmart lot.
Right.
Early in the morning after it's rained. You see those iridescent sheens from oil drips, maybe bits of tire rubber, just general grime and dust.
Yeah, all that stuff that accumulates.
On a normal road, rainwater just washes all that straight into the nearest drain and then into rivers or lakes. But porous pavements, they act like a giant filter. The water seeps through, but the pavement structure itself traps a lot of those pollutants, the oils, the heavy metals, the sediments.
It's quite effective, actually. The pavement structure and the layers underneath can break down some pollutants over time, too.
So it cleans the water passively. That's huge.
It is.
And the third big one, heat island mitigation. We all know dark asphalt gets incredibly hot in the summer,
Well,
right?
yeah. Radiates heat long after the sun goes down.
It contributes massively to that urban heat island effect, where cities are degrees warmer than surrounding rural areas. Porous pavements help because water retained within those voids evaporates.
Evaporative cooling, basically.
Exactly. It actively cools the pavement surface, which helps lower the ambient air temperature.
And if you look at the big picture, these 3 benefits, runoff reduction, pollution control, cooling, they tie directly into creating more sustainable, resilient cities. It's a multi-pronged positive impact.
Okay, so it sounds amazing, but it's not all roses, I assume. There must be limitations.
That's right. They're definitely not a one-size-fits-all solution. You wouldn't use them everywhere. Specifically, they aren't suitable for high-volume, high-speed roads. Think interstates, major state highways.
Why is that?
2 main reasons. First, at high speeds, the force of tires can actually pull small stones, the aggregate, out of that open mix. It's called raveling or traveling.
Okay, that sounds bad. Like the road surface is coming apart.
It can be, yeah. Not ideal for safety or durability on a busy highway. Second, the structure itself. Porous asphalt, because of those voids, is inherently a bit weaker than standard dense graded asphalt, maybe around 10% less strong structurally.
So it just can't take the constant heavy loads of something like interstate truck traffic.
Precisely. The structural design reflects that. Its layer coefficient, basically how much strength it contributes to the overall road structure, is a bit lower.
Got it. So no porous interstates anytime soon.
Probably not.
But where do they make sense? Where do they really shine?
Their sweet spot is definitely in lower speed, lower volume areas. Think residential streets, parking lots, bike paths, maybe some low volume county roads.
Okay. And is there still a big potential impact there?
Oh, absolutely. Let me give you an example. Take Arkansas.
Okay.
Arkansas has about, say, 2,500 lane miles of interstate highways, high speed, high volume, but it has around 27,000 lane miles of county roads.
Wow, more than 10 times as much.
Exactly. So even if porous pavements aren't right for that small fraction of interstates, there's this vast network of county roads, residential streets, parking lots where they could be incredibly effective. The potential scale is still enormous.
That really puts it in perspective. So, okay, we know where and why. Let's dig into how they're actually built. What's underneath that porous surface? Let's build it from the ground up.
Sounds good. It's really a whole engineered system designed for water management. So starting at the very bottom, you have the uncompacted subgrade. That's the native soil.
Uncompacted. Usually, don't they pack the ground down tight before building a road?
They do for conventional roads to make it stable and prevent water from weakening it. But here, we want the water to infiltrate into the ground. Compacting soil makes it denser, increases runoff. Leaving it looser helps water soak in.
Ah, okay, so you leave the natural soil more permeable.
Correct. Then, often placed right on top of that subgrade, is a geotextile fabric.
Like a sheet of special cloth.
Sort of, yeah. It's permeable to water, but its main job is separation. It stops the fine soil particles from the subgrade from migrating up and clogging the voids in the layers above it over time.
Gotcha. Keeps the system from getting plugged up.
Exactly. Above the fabric is the real heart of the storage system, the stone reservoir. This is a thick layer of clean, large, single-sized crushed stone. Think like gravel, but specifically chosen for size and lack of fine dust.
Single size, so there are big gaps between the stones.
Precisely. Because there are no smaller particles filling the gaps, this layer can have a very high void space, up to 40%. This is where the water temporarily collects after it passes through the surface. It's the main storage tank, essentially.
40% void space is huge. That can hold a lot of water.
It really can. Now, sometimes between this big stone reservoir and the final surface layer, there's an optional choker course.
Choker core?
Yeah, it's usually a layer of smaller, single-sized stone. It acts as a stable platform for placing the surface course and prevents the hot asphalt or concrete mix from sinking down into the very large voids of the reservoir below during construction.
Kind of like a transition layer.
Good way to put it. Then finally, you have the surface layer itself. The porous asphalt or porous concrete you actually drive or walk on, that's the layer with the 15–25% voids we talked about earlier.
And that lets the water in initially.
Correct. And one more optional feature. Sometimes you'll see a stone edge or edge drain along the side. This provides some lateral support, especially for asphalt, and can act as an overflow if the main reservoir gets completely full.
So it's this whole layered system designed to capture, store, and slowly release water right where it falls.
That's the key idea, on-site infiltration. Instead of shedding water rapidly to a ditch or pipe somewhere else, you manage it right there, letting it soak naturally into the ground. It mimics the natural water cycle much more closely.
It's pretty ingenious when you break it down like that. But building it right must be critical. You can't just eyeball it, I imagine. What do engineers need to consider?
Absolutely not. Design is crucial for success. There are three main buckets of considerations. First, site conditions. You have to know what you're building on. How deep is the bedrock? Is there enough room for water to go down?
Right. Can't infiltrate into solid rock.
Exactly. What's the soil type? Clay soils drain much slower than sandy soils, so that affects how quickly the reservoir empties. Soil characteristics matter a lot. And even the slope of the pavement is important. Even porous pavement will shed some water laterally if it's steep enough.
Okay, so site assessment is step one. What's next?
Second, hydrology design. This is about water quantity. How much rain are you designing for? Based on local rainfall patterns, you calculate the required storage volume for that stone reservoir. You need to make sure it can handle a typical storm event without overflowing under the surface. That's also where designing those optional edge drains comes in. They act as a safety valve.
Makes sense. Handle the expected water volume. And the third?
Third is structural design. How strong does the pavement need to be for the expected traffic? Engineers use standards, like the 1993 AH2 Design Guide, that's the American Association of State Highway and Transportation Officials. It provides methods to calculate the required thickness of each layer.
Okay. And does the slightly lower strength of porous asphalt factor in here?
Yes, significantly. The calculation often involves something called a structural number, SN, which sums up the contribution of each layer. Each layer type has a structural coefficient A. Standard dense asphalt might have an A value of 0.44. Porous asphalt's A value is slightly lower, maybe 0.40 to 0.42, reflecting that reduced strength due to the voids.
So engineers compensate maybe by making the porous layer thicker or the base layers stronger.
Exactly. The design ensures the overall structure is robust enough for its intended use, even with the slightly weaker porous material, which, brings up a really important point. How do we actually measure the environmental benefits we've been talking about? How do we put numbers on it?
Yeah, that's the crucial question, isn't it? We've talked about the structure, the benefits in theory.
Mm-hmm.
But what does the data show? How can we actually quantify the impact?
Right. Let's look at some key metrics engineers use. One common one is the runoff coefficient, usually called C. It represents the fraction of rainfall that becomes surface runoff. For traditional asphalt or concrete, C is very high, typically around 0.95, meaning 95% of the rain runs off.
Almost all of it.
Pretty much. But for porous pavements, studies show C's values ranging anywhere from 0.12 up to maybe 0.67.
Wow, that's a massive difference. Even at the high end, 0.67, that's still way less runoff than 0.95.
A significant reduction, yes. Another measure used, particularly in certain hydrology models like the NRCS method, is the curve number, or CN. Higher CN means more runoff. Standard concrete might have a CN around 98, very high. Porous concrete. Studies show CN values down around 77.
Again, a big drop. So let's make this concrete, no pun intended. Let's use that NRCS method example. Imagine we have a parking lot and it gets, say, 2.6 inches of rain in a storm. What's the difference in runoff between standard concrete and porous concrete?
Okay, well, without getting lost in the specific formulas, if you run the calculation using those typical CN values, that standard concrete parking lot with a CN of 98 would generate about 2.37 inches of runoff from that 2.6-inch storm.
So most of the rain runs off.
Yes. Now, the porous concrete parking lot with its lower CN of 77, it would only generate about 0.80 inches of runoff from the same storm.
Hold on. So 2.37 inches versus 0.80 inches.
Correct.
That's a difference. 1.57 inches less runoff just
Yeah.
by changing the pavement type.
Exactly. That 1.57 inches of rain per storm event is instead soaking into the ground, recharging groundwater, not overwhelming storm drains.
That's the aha moment right there. It clearly demonstrates the tangible environmental benefit. That's not a small change.
Not at all. Multiply that effect across thousands of parking lots and residential streets, and the cumulative impact on reducing runoff and pollution is huge.
So wrapping this up, porous pavements really are a powerful tool in the toolbox, an innovative way to manage stormwater, cut down pollution, even cool our cities. They're not for every single road, definitely best suited for those lower traffic areas like neighborhoods and parking lots, but the potential seems immense.
It really is. And stepping back, understanding these kinds of solutions like porous pavements, I think it's vital for anyone interested in how we build more sustainable, more resilient infrastructure. It's about being aware of the smart engineering that can make our urban environments better places to live.
So here's something to think about as you go about your day. Look at the ground beneath your feet, beneath your car wheels. Consider those vast stretches of pavement. How could adopting more of these invisible solutions, like porous pavements, start to reshape our communities? Not just managing water better, but creating fundamentally cooler, cleaner, healthier urban spaces. What small changes in your own area could start to add up to a big difference? Something to ponder.